In 1609 and 1618, Johannes Kepler published his laws of planetary motion, heralding great advancements in our understanding of our solar system and the universe as a whole through the use of large amounts of collected data. Today, we will briefly illustrate and examine Kepler's 3 laws of planetary motion. 1. We start with the Sun. Let's shrink it a little bit to make the diagram clearer. It is obviously not drawn to scale. When we trace the orbit of a planet like the Earth, we generally assume that the orbit is circular. And yes, for those of you who have studied the physics of gravity and centripetal acceleration, you know it is indeed possible for the orbit to be perfectly circular. However, reality is often not so perfect, and the orbits will actually be a little stretched. I have exaggerated this effect. The Earth's orbit does look quite circular, but the path is indeed stretched. In fact, it's an ellipse. Now, if the orbit is elliptical, what is special about the Sun's position? Well, it is located at one of the foci of the ellipse. Remember that an ellipse has 2 foci, so the Sun occupies one focus. And that is Kepler's first law. A planet revolves around the Sun in an elliptical orbit, with the Sun at one focus. Two. Let's take a look at Kepler's second law. Start by drawing out an orbit around the Sun. As we saw with Kepler's first law, the orbit is elliptical with the Sun at one focus. Now, let's add a planet to the orbit and track its motion. If you look at its motion, you will notice that the planet moves faster when it is closer to the Sun and slower when it is farther away. Again, the effect is exaggerated here to show it more clearly. Now, let's see what Kepler's second law says. It states, the line joining the Sun to a planet sweeps out equal areas in equal times. Well, what does this mean? To illustrate this, let's shrink the diagram and split it into 8 pieces. Let's say that the orbit takes 8 seconds to complete and each piece represents 1 second of it. We essentially break the orbit into 8 pieces, each taking an equal amount of time. We start with the top right, 1 second, another second. As the speed of the planet changes as it moves through its orbit, so does the length of the arc it traces out. If we instead look at the sector, which is highlighted in each diagram, we see that the areas of each sector are roughly equal. And that is Kepler's second law. Each of those sectors will have exactly equal area. Three. Finally, we have Kepler's third law. It states, the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. It may be easier to express it in equation form. T squared equals Ka cubed. Alternatively, this equation is equivalent to a cubed over t squared is equal to k. Here, t is the orbital period, a is the length of the major axis, and k is a constant. Essentially, what this tells us is that as the length of the major axis increases, the period of the orbits also increases at a faster rate. And there we have it, Kepler's 3 laws of planetary motion. 1. A planet revolves around the Sun in an elliptical orbit with the Sun at one focus. 2. The line joining the Sun to a planet sweeps out equal areas in equal times. 3. The square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit.